Welcome everyone. In my previous video, I have discussed the question of steel structures from Gupta and Gupta book up to question number 150. Today I am going to discuss question number 151 to 200 in this video. So let's start. Question number 151. Consider the following statements regarding tensile test diagrams for carbon steels with varying carbon contents. As the carbon content increases, Statements 1. The ultimate strength of the steel decreases. Statement 2. The elongation before fracture increases. Statement 3. The ductility of the metal decreases. Statement 4. The ultimate strength increases. So out of these 4 statements, which statements are correct? So let me tell you, tensile tests are used to characterize the mechanical properties of the material including carbon steel, okay, and it is also used to provide the information between the stress strain relationship of the material, and carbon is the strength hardening element in the steel, okay. So if the carbon content increases into the metal, then the ultimate strength of the steel will increase, okay, and if the carbon content of the steel increases, the steel will be brittle in nature than before. So the elongation cannot be in that amount as expected, so resulting in decreasing the ductility of the metal. So statements 3 and 4 are correct. Option A is right answer. Question number 152. Consider the following factors. Factor 1. Large number of loading cycles. Factor 2. Large variation in stress. Factor 3. Large stress concentrations. Those associated with fatigue failure would include all the factors, because fatigue failure is the type of failure that occurs in a body, in a material, when it is subjected to repeated or cycle of load in large concentration and large variations. So if any material undergo fatigue failure, then it will obviously experience large number of loading cycles, large variation in stress and large stress concentrations. So option D is right answer. 1, 2 and 3. Question number 153. In industrial buildings in the northern hemisphere, the advantage of north light roof is that it permits diffused daylight into the building and helps to avoid glare of the direct sunlight. Option C is right answer. Question number 154. In plastic analysis for flexure, which of the following pairs of shape of section and shape factors are correctly matched? So for I section it will be 1.14, so it is not matched. For square section and rectangular section it will be 1.5, right, it is matched. And for circular section it will be, that means shape factor will be 1.7, so it is matched. So option B is right answer. 2, 3 and 4 are correctly matched. Question number 155. A single angle tie in a welded steel roof truss of an industrial building is subjected to an axial tensile force of 60 kN. If the yield stress of the material is 250 MPa or Newton per millimeter square, then the section that would best satisfy the requirement of IS 800 is. Suppose this is the Indian standard angle section, one leg and this is another leg, okay. So by the data from the question, the axial tensile force is equal to 60 into 10 to the 3 Newton and axial tensile stress is equal to 0.6 into yield stress of the material, okay. So 0.6 into 250 Newton per millimeter square. So we can calculate the net effective area of this section is force divided by this stress, so it will be equal to 400 millimeter square. Now in another way we can calculate the net effective area of this section. A net equal to A1 plus A2 into K. A1 is the area of this leg, A2 is the area of this leg, and K is the factor, that is equal to 3A1 divided by 3A1 plus A2, okay. Here A1 equal to A2, so the area will be equal to thickness T into L minus T by 2, okay. L is the length of the leg and T is the thickness of the section, okay. So we will choose the section from option A. The section is ISA 50 into 50 into 5. So A1 and A2 will be equal to each other, so which is equal to thickness t equal to 5 into L equal to 50 minus t by 2 5 by 2, which will be equal to 237.5 millimeter square. And if we calculate the value of K will be 0.75, so the net effective area will be 415.6 millimeter square. Similarly, the section given at option B, ISA 50 into 50 into 6, the A1 A2 will be 282 millimeter square. The net effective area will be 493.5 millimeter square. Same way, option C, the section is ISA 50 into 50 into 5. So the area A1 A2 will be equal to 262.5 millimeter square, and the net effective area will be 459.3 millimeter square. Okay. And similarly, at option D, the section is 55 into 55 into 6. So the area A1 A2 will be equal to 312 millimeter square, and the net effective area will be 4546.6 millimeter square. So we will choose the best section. By the data from the question, we got the net effective area 400 millimeter square. So we will choose the section whose area is close to this area. So section A, ISA 50 into 50 into 5, whose area 415.6 millimeter square, close to this area. So this section will be very effective in case of steel roof of industrial building, because it will also be economical. Okay. Now others area and other section whose area are larger than this, these sections are uneconomical. Okay. So the section given at option A, 50 ISA 50 into 50 into 5, is the right answer. Next, question number 156. Apart from gravity loads, which of the following loads are considered in the design of gantry girder located within an industrial building? Longitudinal loads and lateral loads. Both loads are correct, option 2 and 3. So option C is right answer. Question number 157. The angle of dispersion of a concentrated load on the flange to the web plate of a steel beam is 45 degree with the horizontal. Option C is right answer. Question number 158. Which of the following methods of design would be suitable for metal structure subjected to stress, reversal and impact? Simple working stress design, semi-rigid design, elastic rigid design. 1, 3 and 4 method will be suitable for metal structure subjected to stress, reversal and impact. Option B is right answer. Number 159. A welded steel plate girder consisting of two flange plates of 350 mm into 16 mm and web plates of 1000 mm into 6 mm requires. Suppose this is the welded steel plate girder. This is top flange of dimension 350 into 16. And this is bottom flange of dimensions 350 into 16, and this is the web plate of dimension 1000 into 6. 1000 is the clear depth and 6 is the thickness. So here the depth of web of this plate girder will be 1000 mm and thickness of web, that will be equal to 6 mm. Okay, so if we make the ratio d by tw, dw by tw, we will get 166.66. and also we know that if the ratio is less than equal to 85, then no stiffener is required. But if the ratio is greater than 85 and less than 200, then vertical stiffener is required. So intermediate vertical stiffener is required for this welded steel plate girder. Option C is right answer, intermediate vertical stiffeners. Question number 160. The following observations refer to two metal specimens A and B of the same size subjected to uniaxial tensile test up to failure. Observation 1. The elastic strain energy of A is more than that of B. Observation 2. Area under stress strain curve of A is less than that of B. Observation 3. The yield strength of A is more than that of B. Observation 4. The percentage elongation of A and B are equal. Option C is right answer. The ductility of the two specimens is equal. Question number 161. Consider the riveted joint shown in the figure 13.8. The maximum permissible value of pitch P, where rivet diameter is 220 mm, is. For this riveted joint connection, the force is compressive. So for compression, the pitch is 12T or 200 mm, whichever is less, where T is the thickness of thinner outside plate. So T is the 6 mm. Pitch value will be 12 into 6, that means 72 mm. Option C is right answer. Question number 162. Synthetic rubber used for elastomeric bearings should have respectively hardness and ultimate tensile elongation of 65 and 350%. Option B is right answer. Question number 163. A steel plate is 30 cm wide and 10 meter thick. A rivet of nominal diameter 18 mm is driven. The net sectional area of the plate is. Suppose this is the plate of length L and width 30 cm and thickness 10 mm. So we have to find out the net sectional area of this plate. So this section, okay, width 30 cm and thickness 10 mm or 1 cm. So the formula for net sectional area of this plate will be B bracket B minus N into D into T. N is the number of rivet, N is the number of rivet hole, D is the diameter of the rivet hole, and B is the width of the plate, and T is the thickness. B is 30 centimeter, T is 1 centimeter, N is equal to 1 because one number of rivet of one rivet hole is there, and D is the diameter of the rivet hole, which is equal to 18 plus 1.5 mm. So D will be equal to 19.5 mm. If we put all the value into this equation, we will get the net sectional area of this plate equal to 28.05 centimeter square. Option C is right answer. Question number 164. A cantilever steel beam of 3 meter span carries a uniformly distributed load of 20 kN per meter, inclusive of self weight. The beam comprises ISLB 200 at the rate 198 Newton per meter. Flange is 100 mm into 7.3 mm. Wave thickness 5.4 mm. And the moment of inertia Ixx equal to 1696.6 cm to the power 4 and Iyy equal to 115.4 cm to the power 4. Bending and shear stresses in the beam are respectively. Suppose this is the cantilever beam subjected to uniformly distributed load 20 kN per meter of span 3 meter. So maximum bending moment we know will be at here, which is equal to WL square by 2. 20 into 3 square by 2 equal to 90 kN meter. So the section modulus Z max will be I max divided by small d by 2. Z max will be equal to 1696.6 into 10 to the power 2 millimeter cube. And maximum bending stress sigma max will be equal to bending moment M divided by Z max section modulus. If we calculate, it will be equal to 530.47 Newton per millimeter square. We also know that the maximum shear force on this beam will be W into L. So 20 into 3 equal to 60 kN. So the maximum shear stress tau max will be equal to V by TW into depth of the beam. So shear force value V equal to 60 into 10 to the power 3 divided by 5.4 into 200. TW is the thickness of the wave. So tau max will be equal to 55.5 Newton per millimeter square. So option A is right answer. Number 165. Which one of the following is the most important consideration in the design of a repeated joint between structural members when the centroid of the rivet does not coincide with the axis of the load? Option C is right answer. The shear force caused in each rivet due to eccentricity of the load is proportional to the radial distance of the rivet from the centroid of the rivet group, and the maximum resultant force in any rivet should not exceed the rivet value. Question number 166. The common assumption that all rivets share equally a non-eccentric load is valid at a load equal to the failure load. Option D is right answer. Question number 167. At the location of plastic hinge, curvature is infinite. When a structure undergoes plastic deformation, the plastic hinge is formed, which is a location where material has yielded and cannot retain its original shape. At this location, the curvature is infinite. Option B is right answer. Question number 168. Jet purlins may be fixed in either orientation A or B, as shown in the figure 13.9. So which one of the following statements is correct in this regard? Option C is right answer. Both the orientation are structurally equally efficient. Question number 169. For an I-beam, the shape factor is 1.12. The factor of safety in bending is 1.5. If the allowable stress is increased by 20% for wind and earthquake loads, then the load factor is. We know that factor of safety equal to yield stress divided by allowable stress. So Y by A. So yield stress equal to Y and allowable stress equal to A. So new factor of safety after increase of 20% in allowable stress, it will be y divided by 1.2 into a, which is also equal to factor of safety divided by 1.2. We also know that load factor equal to factor of safety into safe factor. So factor of safety will be new factor of safety, that is equal to factor of safety divided by 1.2 into safe factor of the I beam equal to 1.12. So if we put the value into this equation, we will get load factor equal to 1.40. Option D is right answer. Question number 170. Intermediate vertical stiffeners are provided in plate girder to eliminate wave buckling. Option A is right answer. Question number 171. Consider the following statements. Aluminium is being increasingly used for structural purposes because its modulus of elasticity is double that of steel. Its coefficient of thermal expansion is half of that steel. It requires less maintenance, and the strength to unit weight ratio of aluminium is high. Both statement 3 and 4 are correct. It requires less maintenance and the strength to unit weight ratio of aluminium is very high. Question number 172. The weakest plane in a fillet weld is the one along the throat. Option C is right answer. Question number 173. The figure 13.10 shows a portal frame with loads. All members of frame have same plastic moment of resistance MP. The value of W at collapse load will be. So for this portal frame, we have to find out the value of collapse load. Okay. This is the vertical load, this is the horizontal load. We have three mechanisms: beam mechanism, sway mechanism, and combined mechanism. Okay. So number of independent mechanism N will be equal to capital H minus capital R, where a capital H is the plastic hinges possible, that is equal to 5, and capital R is the degree of redundancy or static indeterminacy, which is equal to R dash minus 3. R dash is the number of reaction components from these two supports, that is equal to 6 minus 3 that is equal to 6. So capital R will be equal to 6 minus 3 equal to 3, and capital H plastic hinge, that will be at 5 positions at fixed support at the point where point load acts and at the joint. Okay, so plastic hinge will be at here, at here, at here, at here, and also at here. So 5 possible hinges. Okay, so the number of independent mechanism will be 5 minus 3 equal to 2. Okay. So we have to find out the value of collapse load for this portal frame, and we have three mechanism. First one is beam mechanism. So collapse diagram for this beam mechanism will be for this horizontal part like this. The load is at the center, so this length is also equal L by 2, and the collapse load at here. So internal work done will be equal to moment into rotation. So plastic moment is constant throughout this frame. So plastic moment MP into theta at here, and plastic moment MP into 2 theta, because this angle will be 2 theta. If this angle is theta and this angle is also theta, so this angle will be 2 theta. So MP into 2 theta, and at this point the internal work done will be MP into theta. So total 4 MP theta, and external work done WE will be equal to load into deflection. So load at here is 2W and deflection is at here L by 2 into theta. So WL into theta. So by the principle of virtual work, if we equate equation 1 to equation 2, we will get collapse load W is equal to 4 MP by L. Now sway mechanism. For this mechanism only horizontal load is considered and the vertical part will be considered. So this is sway mechanism. The load is at here. This length is L by 2, this length is L by 2. So internal work done will be at here MP into theta, at here MP into theta, at here MP into theta, and at here MP into theta. So 4 MP theta, and external work done will be load into deflection. So at here load W and deflection is L by 2 into theta. So W L by 2 into theta. So by the principle of virtual work, if we equate equation 3 to equation 4, we will get collapse load W equal to 8 MP by L. Now next, combined mechanism. Combined mechanism is nothing but the addition of these two mechanisms. So collapse diagram is like this. So internal work done will be MP into theta plus MP into theta plus MP into 2 theta plus MP into theta plus MP into theta. So 6 MP theta, and external work done will be equal to this work done plus this work done. So 1.5 into WL theta. This is equation 5, this is equation 6. By the principle of virtual work, if we equate equation 5 to equation 6, we will get collapse load W equal to 4 MP by L. So lowest load from these three mechanism is considered as the collapse load for the frame, and it is 4 MP by L. Option B is right answer. Question number 174. A rectangular steel section of width B and depth h has been stretched up to yield point sigma y up to a depth of h by 4 from both top and bottom face under the action of a moment m. The magnitude of the moment m is. This is the stress diagram for a rectangular beam section when moment equal to yield moment, when moment is greater than yield moment but less than plastic moment, and when moment is equal to plastic moment, then the diagram is like this. So this is the stress diagram where rectangular steel section stretched up to a depth of h by 4, okay, and with B. This is the rectangular portion and this is the triangular portion. Same is at here at tension side, okay. So the area of compression and area of tension will be same, so that will be equal to area of this rectangular section and plus area of this triangular section, that will be equal to 3bh by 8. And now we have to find out the distance between center of gravity of this whole section and the neutral axis. So for this we know the formula from center of gravity. Suppose this portion area is A3 and this portion area is A4, and the distance between neutral axis and this CG of this section is Y3, and the distance between neutral axis and the CG of this triangular portion is Y4. So we know the formula for center of gravity from neutral axis will be A3 Y3 plus A4 Y4 divided by A3 plus A4. So by this formula we will get Y1 Y2 equal to 11h by 36. Now moment, we know the formula for moment, plastic moment equal to sigma y stress into AC into Y1 plus sigma y into AT area of tension section and Y2 sigma y into AC into Y1 plus sigma y into AT into Y2. We know AT equal to AC and Y1 equal to Y2, that is equal to 11h by 36, and AC and AT is equal to 3bh by 8. So if we put all the value in this equation, we will get the moment MP equal to 11b h square by 48 into sigma y. Option C is right answer. Question number 175. A simply supported beam of span L supports a concentrated load W at its midspan. If the cross section of the beam is an I section, then the length of the plastic zone of the plastic hinges will be. A simply supported beam of I section subjected to a concentrated load P at its middle or center. Okay, the bending moment diagram will be like this. Okay. Suppose at this point left of this load the yield moment is at here, and at this point at the right of the load the yield moment is at here. So the distance between this point to this point is known as elastoplastic zone or length of elastoplastic zone. Okay, so the formula for finding out the length of elastoplastic zone, LP, is equal to L into 1 minus 1 by F, where L is the length of span and F is the shape factor of the beam cross section. Beam cross section is the I section, so F will be equal to 1.15 and length of the beam is L, so plastic elastoplastic length LP will be equal to L by 8 nearly. Option A is right answer. Question number 176. A continuous beam of constant MP has a 3 equal spans and carries total uniformly distributed load W on each span. The value of collapse load for the beam will be. This is the continuous beam of UDL load W on each span A, B, C, D. For this beam, the plastic hinge will form at the middle of this load at here, at the middle of this load at here, and at a distance 0.414 L from D. The plastic hinges will not occur at A and at D because they cannot take moment. For span AB, the collapse diagram is like this. If this angle is theta, this angle is theta, so this angle will be 2 theta. So average work done, average external work done will be equal to load into deflection. So load W into deflection L by 2 into theta divided by 2, because it is UDL, so it will be average. So average external work done will be WL by 4 into theta. This is equation 1. And internal work done will be at here and at here. At here it will be nil because plastic hinge does not form here. So internal work done will be at here MP into 2 theta plus MP into theta. So 3 MP theta, that is equation number 2. So by the principle of virtual work, if we equate equation 1 to equation 2, we will get the collapse load equal W equal to 12 MP by L. Now for span BC, the collapse diagram is like here. This is theta, this is also theta, and this angle will be 2 theta by the principle of geometry. Okay, so average work done, average external work done will be equal to W into L by 2 into theta, W into L load into deflection, W into L by 2 into theta divided by 2, because it will be average and it is at uniformly distributed load. So this is equation number 3, WL by 4 into theta. And the internal work done will be moment into rotation at here MP into theta, at here MP into theta, and at here MP into theta. So 4 MP theta, that is equation number 4. So by the principle of virtual work, equation 3 equal to equation 4. So we will get collapse load W equal to 16 MP by L. For span CD, the collapse diagram is like here. This angle and this angle will be different because the plastic hinges form at a distance 0.414 L from this far end. Okay, so this angle is theta, so this angle is alpha, so this angle will also be theta plus alpha by the principle of geometry. So we can also write 0.586 L theta, this length is 0.58 L theta, and this length is 0.414 L alpha by the equilibrium. So alpha will be equal to 0.586 theta divided by 0.414. Now average work done, W will be equal to W into 0.414 L theta by 2, that is equation number 5. And internal work done will be at here MP into theta and at here MP into theta plus alpha, and there will be no internal work at here because plastic hinge does not exist here. So internal work done will be equal to MP into theta into 1.414 divided by 0.414, that is equation number 6. By the principle of virtual work, equation 5, if we equate equation 5 to equation 6, we will get collapse load W equal to 11.656 MP by L. That is the lowest between 3 span AB, BC and CD, and the lowest load that will be considered as collapse load for the beam. Question number 177. A channel section is placed in an inclined position carrying vertical loads as shown in the figure 13.11. If the applied moment for the channel is M due to vertical load, then Mxx is given by. For this channel section, if this is the plane of loading and the applied moment for this channel is M, the moment Mxx will be M into sin 30. So Mxx is equal to M by 2. Option B is right answer. Question number 178. The thickness of wave for unstiffened plate girder with clear distance small d between the flanges shall not be less than d by 85. Option B is right answer. Question number 179. What is the effective net width of plate shown in the figure 13.12 for carrying tension. So diagram of the plate is like this, and this is G1 gauge distance, and this is G2 gauge distance. This is edge distance 1, edge distance to E2. This is S1 spacing, and this is S2 spacing, both equal to 50 mm, and width of the plate is 300 mm, and there are 3 number of rivet hole, that is equal to dia 25 mm. The formula for neat area of this plate will be T into B minus ND plus S1 square by 4G plus S2 square by 4G. We know all the value. T is the thickness of this plate, and if we calculate the neat width of this plate, so if we put the value in this formula without thickness, the neat width of the plate will be 237.5 mm. Option B is right answer. Question number 180. For the beam shown in the figure 13.13, the collapse load P is given by. This is the fixed beam subjected to a concentrated load P at center. This is plastic moment MP, and this is plastic moment 4 MP to a distance L by 4. We have to know where the plastic hinge will form. Plastic hinge will form at the fixed support at both, and at the point where point load occurs at here, and at the point where section changes. The section changes the moment capacity MP to 4 MP, so at here. So for this load, so under this load, the collapse diagram is like this. This is theta, this one will also be theta, so this angle is 2 theta. So external work done WE will be equal to load into deflection P into L by 2 into theta, PL by 2 into theta, equation 1. And the internal work done equal to moment into rotation. So at here MP into theta, at here MP into 2 theta, and at here 4 MP into theta. So 7 MP theta, that is equation number 2. So by the principle of virtual work, the equation 1 is equal to equation 2, and we will get the collapse load P equal to 14 MP by L. Now for the change in section, the collapse diagram is like this. Okay, because the section change here at a distance. So this angle is theta 1, this angle is theta 2. So this angle will be theta 1 plus theta 2. So we can also write theta 2 into L by 4 equal to theta 1 into 3/4 by L. We will get theta 2 equal to 3 theta 1. Now external work done WE will be equal to load into deflection P into L by 2 into theta 1. So P into L by 2 into theta 1, that is equal to equation number 3. Now internal work done will be at here MP into theta 1 plus MP into theta 1 plus theta 2, and plus at this point 4 MP into theta 2. So if we calculate by putting theta 2 equal to theta 3 theta 1 at this equation, we will get internal work done WI equal to 17 MP theta 1, that is equation number 4. So by the principle of virtual work, if we equate equation number 3 to equation number 4, we will get collapse load P equal to 34 MP by L. Now the lowest value is considered as value of collapse load. So this one is lowest 14 MP by L. This is the collapse load for this fixed beam. Option B is right answer. Question number 181. A fixed beam as shown in the figure 13.14 is loaded with UDL over the entire span. The total load being W. When load was just increased to W1, the deformed shape as shown in the figure 13.14 was seen. The value of W1 plastic moment of resistance is MP, and this is the fixed beam of UDL W1 of span L. For this beam, the plastic hinge will be at here, will be at the middle of this load UDL, and will be at the fixed support at here. Okay, so if we draw the collapse diagram for this beam, it will be like this. This angle is theta, this angle is theta, so this angle will be 2 theta by the geometry. Average external work done will be load into deflection. So at this point will be load is W1 into deflection L by 2 into theta divided by 2. So W1 L divided by 4 into theta, equation number 1. And the internal work done will be MP into theta, at this point MP into 2 theta, and at this point MP into theta. So 4 MP theta, that is equation number 2. So by the principle of virtual work, if we equate equation number 1 to equation number 2, we will get collapse load W1 equal to 16 MB by L. Option B is right answer. Question number 182. Figure 13.15 shows a typical section of a crane girder. Consider the following statements in this regard. The function of the top channel is to increase the moment of inertia about the vertical axis. Statement 2. Reduce moment of inertia about the horizontal axis. Statement 3. Increase torsional stiffness. Statement 4. Increase lateral buckling strength. Out of this statement 1, 3, 4 are correct. Increase moment of inertia about vertical axis, increase torsional stiffness, and increase lateral buckling strength. Option D is right answer. Question number 183. For a propped cantilever beam of span L with a central concentrated load P, the elastic and plastic moment diagrams are shown in the figure 13.16. From this diagram, it is clear that option B is right answer. Maximum moments are distributed more advantageously in the plastic cases, as hinge formation allows internal bending moments within the structure to be distributed very easily, and the section gets fully stressed under this plastic section, and whole section is fully utilized with some resources. Question number 184. The nail diameter should not be more than T by 6, where T is the least thickness of the wooden member to be connected. Option A is right answer. Question number 185. The stress at which a material fractures under large numbers of reversal of stress is called endurance limit. Option A is right answer. Internal stress which remains in a solid material after the initial stress has been removed is called residual stress. And we know ultimate strength is the maximum strength of a material which a specimen can endure without weakening or failing. Okay. And creep is the increase in strain with constant loading. Question number 186. A ductile structure is defined as one for which the plastic deformation before the fracture is much larger than the elastic deformation. Option D is right answer. Question number 187. Upper yield point in the stress strain curve in structural steel can be avoided by cold working. Option A is right answer. Cold working is a process in which a material is deformed at room temperature. This process increases the strength and hardness of the material. This is because cold working introduces dislocation and strain hardening in the material, which makes it more resistant to deformation. Hot working involves different deformation of material at high temperature, which can produce its ductility and reduce its strength. And quenching is a process in which a material is rapidly cooled from a higher temperature to room temperature to achieve specific mechanical properties. And we know galvanizing is a process of coating a material with a layer of zinc to protect it from corrosion. Question number 188. The most critical consideration in the design of rolled steel columns carrying axial load is the compressive strength based on slenderness ratio and gross cross-sectional area of the member. Option D is right answer. Question number 189. At a section along the span of a welded plate girder where the wave is spliced, the bending moment is M. If the girder has top flange, wave and bottom flange plates of equal area, then the share of the bending moment which would be taken up by the splice plates would be, suppose this is a welded plate girder, this is flange of area A1 and this is bottom flange of area A3 and this is wave of area A2. As per question, A1 is equal to A2 is equal to A3. Okay, the dimension of flange is D into T, and dimension of bottom flange, dimension of top flange is D into T, dimension of bottom flange is also D into T, but the dimension of wave is vertical distance is vertical clear distance is D and thickness is T. Now for this condition to satisfy, we have to use this equation mw divided by m is equal to iw divided by I. That is equation number 1. mw is the moment of the wave and m is the moment of the whole section, and iw is the moment of inertia of the wave, and I is the moment of inertia of the whole section. So the moment of wave will be T dq by 12, and the moment of inertia of the whole section I will be equal to T dq by 12 plus 2 into this top flange and bottom flange, so 2 into T cube D divided by 12 plus D into T in D by 2 plus small t by 2 square. So I will be equal to 7 t d cube by 12, and d cube and d square approaches to 0, so we can say d square and higher value of d is equal to 0. So got iw equal to td cube by 12 and I equal to 7 td cube by 12. So if we put the value into this equation, we will get mw by m equal to 1 by 7. So mw will be equal to m by 7. So option C is right answer. Question number 190. The allowable shear stress in stiffened waves of mild steel beam decreases with increases in the spacing of the stiffeners. Option B is right answer. Question number 191. In the design of frame connection, the rivets or bolts connecting the wave of the beam with the connecting angles are subjected to double shearing and bearing on the wave. Option B is right answer. Question number 192. The effective length of the fillet weight is total length minus 2 into weld size. Option B is right answer. Question number 193. A continuous beam with plastic moment capacities is shown in the figure 13.17. The correct sequence in which the plastic hinges will form in the beam is first at C, then A, then under the load at B. So option A is right answer. Question number 194. A thin hollow box section of 400 mm into 600 mm deep outer dimension with uniform plate thickness of 10 mm all round is used for a beam. The plastic modulus of the section ZP and its shape factor will be. This is the rectangular box section of dimension 400 into 600 and thickness 10 mm. So plastic section modulus ZP, the formula is H into T within bracket B plus H by 2. So H is equal to 600, T is equal to 10 mm and B is equal to 400 mm and H is equal to 600 mm. So ZP is equal to 42 into 10 to the power 5 mm cube, and elastic section modulus ZD is equal to, the formula is H into T within bracket B plus H by 3. If we put the value into this equation, we will get ZD equal to 36 into 10 to the power 5 mm cube. So we know the shape factor. We know shape factor is the ratio of plastic section modulus divided by elastic section modulus equal to 7 by 6. So option D is right answer. Plastic section modulus 42 into 10 to the power 5 mm cube and shape factor is 7 by 6. Question number 195. Figure 13.18 shows a continuous beam loaded with a concentrated load W at the center of each span. The value of W at the collapse will be. For this continuous beam, first we have to select where the plastic hinge will occur. The plastic hinge will occur at here, at here, at here, at here, at here. The plastic hinge will not form at A and at D. This to support A and D cannot take moment. Okay, so for span AB, the collapse diagram is here. This is this angle is theta, so this angle is theta, so this angle will be 2 theta by the geometry. So external work done will be loaded into deflection at this point. So W into L by 2 into theta, so W L by 2 into theta. This is equation number 1. And internal work done equal to moment into rotation. So internal work done will be at here because plastic hinge form at here and will be at here. Plastic hinge will also occur at here. So internal work done at here will be MP into 2 theta, and at here 0.8 into MP into theta because the section changes from MP to 0.8 at this position. The minimum value is considered. So internal work done will be equal to 2.8 MP theta. That is equation number 2. So by the principle of virtual work, if we equate equation 1 to equation 2, we will get collapse load W equal to 5.6 MP by L for the span AB. Okay, now for span BC, the collapse diagram is drawn. The external work done will be equal to WL by 2 into theta as usual. This is equation number 3, and the internal work done is 0.8 into MP theta, 0.8 into MP into 2 theta, and at here 0.8 into MP into theta. The lowest value is considered because the section changes from 0.8 MP to MP, but lowest value is considered. Okay, so internal work done will be 3.2 into MP theta. That is equation number 4. By the principle of virtual work, if we equate equation 3 to 4, we will get collapse load W equal to 6.4 MP by L for span BC. Now for span CD, the collapse diagram is drawn. The external work done will be equal to WL by 2 into theta. This is equation 5, and internal work done will be 0.8 into MP theta plus 0.MP into 2 theta. So internal work done will be total. So total internal work done will be 2.8 MP theta. That is equation 6. By the principle of virtual work, if we equate equation number 5 to 6, we will get collapse load W equal to 5.6 MP by L for span CD. So for span AB, BC and CD, the lowest value is 5.6 MP by L. That is the collapse load for this continuous beam. Question number 196. The roll steel section used in a cased beam has width B mm and diameter D mm. The minimum width of the finished cased beam is given by option B is right answer, capital B plus 100 mm. Question number 197. Given that S is the effective area of the member and sigma y is the yield stress, in order to obtain the ultimate strength of a tension member as per the plastic design concept, AE into sigma y is to be multiplied by 0.85. Option C is right answer. Question number 198. A timber beam of a quick plan L and of cross section B into D is said to be laterally supported if D by B and L by B are respectively less than 3 and less than 50. Option C is right answer. Question number 199. A timber column is made up of two individual members with longitudinal axes parallel, separated at the ends and middle points of their length by blocking and joined at the ends by timber connectors. Such a column is called paced column. Option C is right answer. Built-up columns are composed usually two parallel components connected by lacing or battens, and composite columns are made from two or more different materials such as steel, concrete, timber, etc. And flitch columns are the one where steel plate is sandwiched between the timber plates connected together. Question number 200. A simply supported beam of uniform cross section has span of L and is loaded by a point load P at its mid-span. The length of the elastoplastic zone of the plastic hinge will be. A rectangular simply supported beam subject to a constant load P at the mid-span. Okay, so what will be the length of elastoplastic zone? This is the uniform cross section. So the length is equal to breadth of this cross section of this beam. So suppose this is square section. Okay, so the shape factor is 1.5. So we know the formula, length of elastoplastic zone LP is equal to L into within bracket 1 minus 1 by F. F is the factor of shape factor of the beam cross section. So beam cross section is uniform. Uniform means square cross section. So for square cross section, shape factor is 1.5. So if we put shape factor 1.5 in this equation, we will get the length of elastoplastic zone LP equal to L by 3. Option A is the right answer.